Good morning to everybody. Good morning to all the students. Here we are at our second lecture of the day of our INSPYRE stage. And today we have Lorenzo Maccone. He teaches theoretical physics at the University of Pavia. And today he's giving a lecture on the concept of time in modern physics. So maybe trying to answer to one of the deepest questions that humankind has ever asked: what is time? So please, Lorenzo.
Okay, thank you very much. So let me start. And this is a fish. Of course, you are going to ask, what does a fish have to do with time? Well, think about this fish. He lives in the Mariana Trench. It's about 8,000 meters deep. His universe is like a 10-kilometer cube of water. What would this fish think if we would tell him that stars exist? Just imagine that. And remember the fish. This fish would have to have really an open mind to understand what a star is, because he has never met such a concept. So you're going to meet some very strange concepts of modern physics, and remember the fish, remember to keep your mind open. You're like a fish that has to know about the stars. So what am I going to talk about today? I'll give you some intuition about the strangest and very counterintuitive aspects of time. And the first question, of course, is my title: what is time? Well, take St. Augustine, one of the prime philosophers of time, and he wrote this strange sentence: what is time? If no one asks me, I know. But as soon as I try to explain it, I don't know. Can we do better than this? Can we get a better definition of time? Well, not much. It seems really impossible to define time without using some temporal concepts like before, after, and something like that. If you define time using temporal concepts, of course, you get a circular definition. So time somehow appears to be some sort of primary concept. But of course, time is one of the most used nouns in basically all languages. Like in English, it's in the top 10 nouns used. As if there are any doubts, you're talking about things we don't really know about. Well, what about in physics? What is time? Well, there are two main definitions of time. The first one is time is what is measured by a clock. But of course, then you're going to ask, what is a clock? And you cannot answer me, well, a clock is what measures time, right? Well, okay, this is the first definition. Time is what is measured by a clock. The second definition is a coordinate, something that measures the distance between events. These are the two main definitions of time in physics. And of course, also the second is not really very satisfactory, because as soon as you ask me what is an event, you cannot really define it without using temporal concepts. Okay, so these are the two main meanings we are going to see, but of course there are many other meanings. For example, this on the right is a table taken from Carlo Rovelli's quantum gravity textbook. It lists a huge list of all different concepts of time that are used in science. And this blackboard is a poll that I took on a conference about time. I asked all the scientists present what are their main definitions of time, and we filled a whole blackboard with this. So let's try to see if we can use our definition to understand what time is. And we will see that this is a complete fail. We will not be able to do that. For example, one of the first things that comes to mind is that time flows. And this is not correct. And you can see it very quickly because something flows with respect to something else. Like the river flows with respect to a clock, my heart beats with respect to the river, and so on and so forth. But you cannot say that time flows with respect to what and at what speed. You cannot say that time flows like 1 second per second. You realize immediately that this is meaningless. So the flow of time is an illusion, a confusion between what time is and something that changes in time. So you are confusing like the flow of the river with time itself. And some philosophers even go to the point that they say that time does not exist. For example, Leibniz, McTaggart, Barbour, all these are philosophers that arrive to this drastic conclusion that time does not exist. Leibniz even removed the T apparently from his name to protest against time. So initially his name was Leibniz with the T, but then he was so upset about this time thing that he removed the T from his name. Well, talk about dedication. Anyways, maybe saying that time does not exist is a little too drastic, but for sure, we can conclude that the flow of time is just an illusion. It's not something that we can ascribe to time itself. Time is relational. I'll come back to that. Time is just a relation between different things, like something flows with respect to something else. Another illusion from our intuition is that somehow the present exists, the past does not exist yet, and the future does not exist. The past does not exist anymore, and the future does not exist yet. So that past, present, and future have different essence. I'm not going to go into what it means for time to exist. I'll go back to this later. But somehow we have this intuition that the past, the present, and the future have different essence. And relativity tells us that this is not true. Why not? Well, consider two events which are simultaneous for me. For example, I switch on the lamp and a glass falls. These two events happen at the same time. As I switch on the lamp, the glass falls. Well, do we all agree that these events are simultaneous? No. Well, for an observer that is moving with respect to me, one event happens before, the other one happens after. For him, the observer that is moving, these two events are not simultaneous anymore. Okay, for example, he sees the light switched on and then the glass falling. Of course, these effects are evident only at high speeds. And this is called relativity of simultaneity. So, of course, the relativity of simultaneity means something weird if you apply it to the concept of present, because all the events that are simultaneous to now are the present. But we said that simultaneity depends on the motion. So the present depends on the motion. The present of Alice, who is on the train, is different from the present of Bob, who is at the station. Again, these differences are important only for high speeds. For Alice, the glass falls and the lamp is switched on at the same time. For Bob, they do not happen at the same time. So if past, present, and future have different essence, who should win? Should Alice's present exist, or should Bob's present exist? You realize that this is a meaningless question. It's like saying that the right, the right and the left have different essences. And of course, you're going to ask who's right, because different people see a different direction, right? So the present depends on motion. And Alice and Bob would disagree on what exists and what does not exist. But of course, it's meaningless. So basically, relativity forces us to give the same degree of existence to the past, to the present, and to the future. The physicists talk about this state of things by saying that space-time is a block, the block universe picture of space-time. I cannot divide space from time. For example, considering space at a given time, because simply you have to take space-time as a whole. And relativity has this name because the division of space-time into space and time is relative to the observer. So time and space are not absolute concepts, they are relative. That's why it's called relativity. And in this picture, in this block universe picture, of course, time is just a coordinate that measures some distance between events in the block universe. What did Einstein say about this? Well, he was very, very well aware of this fact. And indeed, he writes, for us who believes in physics, the difference between past, present, and future is just an illusion, however persistent. The interesting thing about this is that he's not writing in a scientific paper. He's not writing this sentence in a scientific paper. He's writing this in a letter to the widow of his friend Michele Besso. He wants to console the widow with this argument about relativity. I'm not sure that the widow was consoled by this, but still it's kind of cute that this idea that comes from relativity, that our relatives which are dead actually have the same degree of existence now as they had when they were alive. So it's kind of nice. Okay, so maybe this would be a nice time to take questions if people have some. People have questions?
Okay. No, there are no questions for now, so I propose to go on. Probably people need some time to break the ice. Okay, good.
So let's go on. So we are saying that the past, the present, and the future have the same degree of existence because otherwise, because these concepts are not absolute, they are relative. So what does it mean to say that time exists? In what sense can we say that? Well, this is a philosophy question. If I block all change and all movement, would time still exist? So if I block everything, what do you think? What would you say? Think about it. Now, what do people say about this? Well, for example, Newton says that absolute true and mathematical time of itself and from its own nature flows equally without regard to anything external. So Newton is saying that time exists even if nothing happens. Of course, not everybody agrees with that. For example, Aristotle, Lucrezia, and Leibniz, famously, who was the antagonist of Newton, says, no, that's bullshit. Time is only relational, a change of something with respect to something else. So time does not exist if nothing happens. It's just a relational quantity. Now, who's right between these two? What do you think? Now, what does physics tells us? That none of the two are right, but in part they are both right. Why? Well, it's true that time exists even if nothing happens, as Newton was saying, because time is a fourth dimensional in relativity, but it's not absolute, it's relative. And also it's true that time is relational, as Aristotle and Leibniz was saying. I can only localize an event with respect to another, but of course, time exists even if nothing happens. Okay, so now a really weird question. If past and future exist, as we saw, can I travel in time? Well, there are two different time travels. One is to the future without return. I will explain what I mean by that. And the answer is yes. It's almost trivial to travel to the future without return. What about time travel to the past? Well, yes, maybe, but only theoretically. I will explain what I mean by that. But let's start with question 1. Can I time travel to the future without return? What does that mean? Well, it means that I arrive to tomorrow before you arrive. So, for example, in a few of my seconds, I arrive to your tomorrow. When we meet again, for me, a few seconds went by, but for you, 24 hours went by. Is this possible? How can we do that? Well, it's very simple. Technically, it's called relativistic time dilation. And it comes out from the fact that time depends on the state of motion. That's why it's called relativity, as we saw. So time in systems that move with respect to us is lower than ours. This somehow means that it is sufficient to move to travel in time. And the answer is yes. And this was one of the first consequences of special relativity. And this, for example, is known as the twin paradox, in which I have two twins, Alice and Bruna, and Alice remains on Earth. Bruna is on a rocket ship, and she leaves, and she travels very quickly. And when she comes back, Alice has aged a lot, while Bruna, who was traveling, has aged very little. Then, if it's so simple, if just movement is sufficient to travel to the future without return, why don't we ever see this in our everyday life? Well, because as all relativistic effects, these become important only if we move at very, very high speeds. So the rocket would have to move at a speed which is comparable to the speed of light. Or otherwise, we can see these effects, but we have to do very, very precise measurements. If you move at slow speeds, you have very small effects. A very famous experiment is the Havele-Keating experiment, performed in 1971. They traveled to the future by 40 nanoseconds, 40 millionths of a second, by traveling billions of a second, by traveling around the world in an airplane. So they were moving at a speed of around 1,000 kilometers per hour. And in this trip, they traveled to the future by only 40 nanoseconds. And of course, you need atomic clocks to measure this distance. These are the atomic clocks. These are Havele-Keating and Hostess during their famous trip. So this has been confirmed experimentally. It's a very real effect. And as I said, these effects are really important when you travel. You have to travel at really high speeds. So how fast do I have to travel to go to your tomorrow in half of your time, if you stand still? Well, if you calculate this, it comes out to 700 billion kilometers per hour, like 200,000 kilometers per second, very similar to the speed of light. This is a picture of the fastest truck in the world. It goes at about like 300 kilometers per hour. You see that that's completely ridiculous with respect to the speeds we are talking about. This truck, by the way, has a turbine engine on it. There's a crazy guy in England that has fun mounting turbine engines on trucks and cars, and this is his truck. Well, anyways, I was saying light moves very fast, and of course, if you want to try to measure light, for example, Galileo tried to measure light, the light speed, and he sent somebody on a mountain, and from another mountain they were trying to measure how fast the light travels between one mountain and another. Of course, this measurement was unsuccessful because light is very fast, and if you do it like this, you would need to see like about a second of time travel between one mountain and another. So how far should he have sent the other person for a time delay of about a second? Well, he should have sent the other man on the moon. That's time travel to the moon is about 1 second for light. Okay, there's also another mechanism for relativistic time dilation. We saw that you can move, but another mechanism is gravity. So time in systems which have a larger gravitational field than ours, time flows slower. For example, if you've seen Interstellar movie, these guys go to a planet which is orbiting around a black hole. You can see the planet here around the black hole. And 1 hour on the planet of the water on this planet is equivalent to 7 years on Earth. That's because this planet is sitting in a huge gravitational field because of the black hole. So does this mean that a person that lives at sea level ages slower because there's more gravity at sea level than a person on the top of a mountain? Yes, the answer is yes. Of course, again, the difference in gravity between sea level and a mountain is very small, so you see a very tiny effect. You even see an effect between your head and your feet. If you're standing up, 1 second for your head is like 1.00001 second for your feet. There are like 16 zeros. So the effect is almost negligible, but your head ages faster than your feet. Why do I say almost negligible? Because even though the difference, this effect is so tiny, there are like 16 zeros, there are some clocks which are so precise that you can measure time to an accuracy of 1 part to 10 to the 18. 1 part, you can measure a difference in 18 zeros. It means that if you lift this clock by 10 centimeters, you're going to see the effect of gravitational time dilation. The new generation of clocks, I was at a conference in San Francisco last year. The new generation of clocks is so sensitive. It has a sensitivity of 1 part to the 10 to the 19. It's so sensitive that it's sensitive to lift by 1 centimeter. The problem is that the clock is larger than 1 centimeter. So you cannot even define time over the dimension of the clock itself. It's really amazing. Anyways, we are saying that these effects are so small. So should we care about this strange time dilation effect? Actually, we should, because we are using it every day. Without relativity, without these time dilation effects, without taking into account these time dilation effects, GPS would not work. Why? Because satellites move very quickly around the Earth, and they are in a weaker gravitational field because they are like 100 kilometers or more of altitude. So basically, the GPS satellites lose 40 microseconds a day, like 40 millionths of a second. It seems like completely negligible, but remember that a microsecond means 300 meters because GPS signals travel at light speed, and light in a microsecond travels for 300 meters. So without relativity, GPS would lose about 1 kilometer per day. So you see immediately that GPS really needs to take into account all these relativistic effects. And indeed, when I was working in the US, I remember we were working on quantum versions of GPS, and we talked to one of the people who developed GPS, and he told us, okay, yes, we are engineers, so for us, general relativity is like a weird theory. I mean, the GPS was developed in the 1960s, so at that time, general relativity did not have many experimental confirmation. So they said the first generation of GPS satellites had a switch to remove all general relativistic effects because we were not sure that general relativities really would matter. But they immediately saw that if they switched off general relativity, the GPS system would not work. It would just fail in like 20 minutes. So it's interesting that this the GPS is one application of general relativity, and general relativity was developed by Einstein as a complete curiosity-driven research. I mean, he was interested in philosophical aspects of time. He was curious about what the nature of time was. He developed general relativity. He was sure that it would never have any practical application. And now, like 100 years later, we are using it every single day. This is the importance of basic fundamental research. Okay, maybe this is, before talking about time travel to the past, this might be a nice time for questions, if somebody has any question.
So, okay, there are a few questions about this quite difficult matter. So the first is from Francesco, who asks, because since simultaneity is relative, this means that we can see the future of a person before that person experiences his future?
No, that's impossible because there are other effects that prevents us from doing that. So that's a very nice question, by the way. We would be able to see this if it was possible to communicate faster than the speed of light. But as far as we know, there is no way to communicate faster than the speed of light. So this means that it's impossible to see in the future of somebody else.
So another interesting question is from Sorush, who asks, if we travel exactly at the speed of light, what happens to the time?
Okay, so another very good question. So, and by the way, this is one of the questions that Einstein asked himself when he was developing special relativity. So it's a really nice question. Well, according to the relativistic laws, it would appear like as time would stop when you travel at the speed of light. But one thing which is very important is that we will never be able to travel at the speed of light, because it turns out that any massive particle or anything that has mass cannot reach the speed of light. Only light itself, which has no intrinsic mass, can reach the speed of light. So we can get as close as we want to the speed of light, but we can never reach the speed of light.
Okay, the last question from Davide is, are astronauts on the International Space Station younger than they should be?
Yes, actually they are. And indeed, I think that, I don't remember the actual numbers, but I think that an astronaut that stays in the International Space Station for a few weeks or months will be like 1 millisecond younger when he comes back to Earth than he would be if he had stayed back to Earth, like 1,000th of a second younger, or something like that. I don't remember the exact numbers, but the answer is yes.
Okay, then there is this very difficult question from Lorenzo. I try to read it. So he says, I know that in mathematics we are able to describe a surface without a coordinate system, but just using the surface itself. Why can't we describe the time in a similar way, just using the properties of time? A bit tricky.
Yes, a bit tricky and a very good question. So there are certainly ways to express general relativity without using coordinates. This is a rather advanced topic. Please, Lorenzo, go and do physics and you will find out. You can use mathematical forms and you can describe relativity without using coordinates. But of course, time, as we saw, time by itself is kind of meaningless because time is one of the coordinates of space-time. So it's one of the components of a space-time vector. So unless you introduce somehow some coordinates or you do some similar tricks, you will not be able to separate time and space inside space-time. Okay, so certainly we can describe shapes without using coordinates. We can even describe general relativity without using coordinates. That was not how Einstein developed it, but it can be done. But still, we kind of need not coordinates, but we need similar mathematical tricks in order to divide space from time in space-time.
Okay, I propose to go on, and then I will collect other questions about this matter. Thanks.
Good. Okay, so now question 2. We saw that we can do time travel to the future without return, but of course, the most interesting kind of time travel is time travel to the past. Can we go to the past? And what did I say? I said yes, maybe, only theoretically. What do I mean by that? Why did I say that? Well, I said yes, because general relativity predicts time travel to the past. We're going to explain this in a second. So this is why I said yes. I said maybe because, first of all, general relativity could be wrong. And this is an idea by Stephen Hawking, for example. And I say only theoretically because even if it's right, even if we can time travel to the past, building a time machine would be basically impossible in practice. So all types of time machine that we know from general relativity require extremely exotic objects, which I think human civilization will never be able to control. Like, for example, you need a rotating black hole, not only a rotating black hole, which is something you can find in the universe, but a black hole that is rotating at relativistic speed. So it's rotating extremely, extremely fast. And this is the simplest way to build a time machine that we know of. There are even much weirder proposals, like using wormholes stabilized with negative energy. I mean, really weird stuff. It's basically impossible in practice to build a time machine. So why do I say that general relativity predicts time travel to the past? This actually was a discovery by Kurt Gödel. He was the greatest mathematical logician of history. He was a great friend of Einstein, by the way. And for Einstein's 70th birthday, Gödel, he was a genius, of course. He was a complete genius, completely crazy, but he was a genius. And for Einstein's birthday, he studied general relativity, the theory that was proposed by his friend. And he discovered this solution to general relativity, which admits time travel. And if you're curious about this discovery, this book by Palle Jurgrau, A World Without Time, tells this story and tells about the friendship between Einstein and Gödel. He was an incredibly smart person. As I said, he was completely crazy. I mean, he convinced himself that somebody was trying to poison him, so he stopped eating. And of course, you can imagine that didn't go so well. So he died of hunger. A very sad story, because he just stopped eating. And of course, the reason why he discovered time travel is also very nice, because apparently his doctor said, okay, Gödel, your mental health, I mean, he discovered the incompleteness theorems, in which he basically proved that there are some things you cannot prove. So he proved there is things that are unprovable. I mean, this is really weird. It's one of the biggest discoveries in mathematics. So of course, thinking of all these paradoxical questions, his mental health was deteriorating. So his doctor said, okay, maybe you should think about something else. And so he took up general relativity. And of course, he discovered time travel and all the paradoxes that come out of time travel. So it just could not help himself. I mean, this guy was really completely... Okay, so Gödel discovered that general relativity predicts time travel. What was Einstein's reply to this? You can find it in the book. You can find Einstein's reply if you're curious. I can give you the reference. He was not very happy about this because, of course, it's a problem for the theory because of the time travel paradoxes, as I was saying. And the answer to Gödel by Einstein says, oh, maybe physics prevents it. And this is more or less what we still think today. As I was saying, okay, this is like a theoretical idea, but it's very difficult to put in practice. So in Gödel's universe, Gödel's solutions to Einstein's equation is a universe that basically rotates on itself. So you're going to ask, if the whole universe rotates, how, with respect to what does it rotate? Okay, I cannot answer this question. The reason why Gödel was exploring this kind of universe is because he was interested in Mach's principle. Mach was saying that all quantities in physics are relative, are relational, and so there are no absolute things in a sense. And so Gödel was trying to see whether he could come up with a universe that rotates with respect to nothing, because the whole universe rotates. And he found this solution. But the interesting part of this solution is not only that it rotates, but that it allows time travel. This universe is really strange. Well, okay, if you're interested, there's a paper in which, this paper here, where you can find some details, but it's a weird universe in which basically the rotation drags the light cone, the causal structure of the universe, of the space-time, so that if you shine a laser, a light beam, in a direction, after some time, the light beam comes back from the opposite side. So light beams travel in a closed loop. You can see here the geodesics, the light rays travel in closed loops. And in this universe, it's possible to have closed time-like curves, which is the technical name for time travel. So if you follow this green trajectory that Gödel calculated, then you can go back to the exact, you can go to any point in space-time. Not any point in space, any point in space-time. And Gödel, he was completely crazy, as I said. He even calculated how much gasoline the spaceship would need to travel along this curve. Okay, now, why did he do that? Well, he wanted to make sure that the gasoline necessary for this trip would not be, you know, that energy is equal to mass. So, and of course, mass curves space. So he was afraid that if you need too much energy, the mass of this gasoline would curve space, would ruin this feature of space-time. But it turns out from his calculation that you don't need that much gasoline after all. It's like 1 or 2 solar masses or something like that. I mean, it's a huge amount, but still it's negligible on a cosmic scale when you're talking about the whole universe. Okay, so what about our universe? Does our universe rotate? Our universe does not. So Gödel even asked some astronomers for the signatures that he was expecting from a rotating universe, and our universe does not have these signatures. So unfortunately, this means we cannot use Gödel trajectories to travel in time. As I said, after Gödel's discovery, other discoveries, other mechanisms for time travel were discovered, like rotating black holes and things like that. But I'm not going to talk about this. What I want to talk about is the temporal paradoxes. So why was Einstein upset about this, the fact that general relativity allows time travel? Well, it's because of the paradoxes, time travel paradoxes, and there are 2 types which are known, the grandfather paradox and the Mona Lisa paradox. Let's start with the grandfather paradox. I go to the past and kill my grandfather before he meets my grandmother. Well, then I cannot be born, so I cannot kill my grandfather. You see that there is a logical contradiction. And of course, we need to avoid that. There are some solutions to this paradox. The first is that time travel is impossible. So, of course, time travel is allowed by general relativity, but we already know that general relativity is not the final theory, because somehow you want to match general relativity with quantum mechanics in order to get the final theory. And if you join general relativity and quantum mechanics, maybe time travel becomes impossible. This is the chronology protection conjecture that was proposed by Hawking. I must say that it does not sound very convincing. It's not convincing at all, I must say. So this mechanism to avoid time travel by joining general relativity and quantum mechanics is not convincing. Why is it not convincing? Because you have time travel in situations like, for example, in Gödel's universe, in which in situations in which the quantum mechanical effects will be basically negligible. So we do not expect to see corrections from quantum mechanics that will prevent you from having time travel. But of course, Hawking is a very smart person, so perhaps he's seeing something I'm not seeing. Another solution is that, okay, time travel is possible, but only the paradoxes are impossible. So there are boundary conditions that imply that in the block universe, the paradoxes will not be possible. This is called Novikov principle, which was developed by Novikov in collaboration with various people. And among the various people, there's also Kip Thorne. He just received the Nobel Prize a few years ago because of gravitational waves, but maybe you know Kip Thorne because he was the scientific advisor for the movie Interstellar. And if you saw the movie, there's a character in the movie which is basically modeled by Kip Thorne. It's not Kip Thorne in the movie, but for example, the blackboards that appear in the movie were written by Kip Thorne, and all the black hole images in the movie are developed in collaboration with Kip Thorne. Okay, the other paradox is the Mona Lisa paradox, which is I take a photo of Mona Lisa to Leonardo da Vinci, who paints the picture by copying my photo. Now, who painted the picture? Leonardo took the picture from me. I gave him a photo, and I took it from him. I took the picture from, I took the photograph from the picture. So basically, the Mona Lisa appeared out of nowhere. So you see that here you don't have any logical contradiction. So this paradox is different from the previous one. But because there is no logical contradiction, these kinds of paradoxes are much more difficult to avoid. And as far as I know, all the solutions to this kind of paradox require quantum mechanics, which is weird. Okay, let me summarize what we have learned from relativity. So we saw that relativity forces us to give the same degree of existence to past, present, and future just because these concepts are relative to the observers. So the past and present and future of Alice are different than the past, present, and future of Bob if Alice is on a train. And another thing we learn is that relativity allows from time travel. And as Einstein said himself in this famous reply to Gödel, this really tells us something very deep about the nature of time. Okay, so maybe this is a good time to stop and take questions.
Okay, yes, there are really interesting questions. So the first is from Giorgio. So in the previous talk, we learned that in quantum mechanics, when we measure something, we also change that system. So Giorgio is asking, at a quantum scale, does a time measurement changes the time itself?
Oh, that's a very difficult question, a very interesting one also. Giorgio, I must tell you the truth. You're going to be disappointed because if you take textbook quantum mechanics, what you will find out is that it says that it is impossible to describe a time measurement. Okay, so time in quantum mechanics appears as a parameter, not as an observable. So basically, the textbook quantum mechanics tells you you cannot describe what is a time measurement. If you go to an experimentalist, they will say, bullshit, we are doing these kinds of measurements all the time. So how come your theory cannot describe these kinds of things? Okay, this is a shortcoming of quantum mechanics. A shortcoming we are actually working very hard to go beyond this. This is also part of my own research. For example, I'm working on this, but it's something which people will not agree. Scientists right now do not know the answer, how we can give a quantum description of a time measurement.
Okay, thanks. Then there has been a few minutes ago, there has been a bit of discussion between the students about the astronauts on the space station. So someone claims that they should be younger because they travel at a high speed, and someone claims that they should be older because they are in a weaker gravitational field. So do you want to clarify this?
Oh, okay, yes, that's a good point. There are two competing relativistic effects. One slows time, the other accelerates time. And I don't know which of these two effects wins, because I don't know. I don't know whether in the end the astronauts are younger or older, but one of the two effects wins over the other. That I know because I've seen some estimates of that. But
okay, then Julia asks, has science ever considered concretely to use time travel?
Oh, there are many scientific papers that explore this. I mentioned these papers by Hawking, the chronology protection conjecture, these papers by Novikov, Kip Thorne, and other people. There's a huge literature on that. So people, and of course also the paper by Gödel, Einstein's reply. I mean, people really are very interested in these questions, but only from a fundamental point of view. They are interested in these questions to understand better what is the nature of time. For practical applications, I would say no. Nobody has ever considered this seriously because, as I said, in practice, it seems to be really impossible. I would say extremely difficult to the point of being practically impossible to build a time machine. So I don't think anybody has ever seriously considered using this time travel for something practical.
Okay, so we can go with the last one, and it is from Cometa. Maybe Cometa has read some Rovelli's book, because she asks, what is thermal time?
Sorry, I mean, you said thermal time.
Yes, thermal time. What is thermal time?
Thermal time, okay, yes. Well, there are, as I said, there are many different notions of time. One notion of time is the one that comes from thermodynamics. And this is a very important aspect of time because it's the only one which in physics gives a direction, a time arrow. So the reason why if we drop an egg on the floor, we get a splattered egg, but we never see splattered eggs that just jump spontaneously back up and become entire eggs by themselves. Or if we drop a glass, the glass shatters on the floor, but we never see the reverse picture. And this is because of thermodynamics, and thermodynamics tells us that entropy, which is a physical quantity that measures this kind of things, is always increases with time. This is one of the very few, maybe the only really one-directional law of physics in time. All the laws of physics, all the other laws of physics we know are bidirectional. So we can reverse the arrow of time and the law still applies. The only one which is not bidirectional is the second law of thermodynamics. And it's not a physical law in the sense like Newton laws or other laws, because it's a statistical law. It's not a deterministic law.
Okay, good. We have so 20 minutes. I propose to go on and then to have a final question time, okay?
Okay, good. So, okay, we saw what happens with relativity regarding time, and what happens if we introduce also quantum mechanics? Somebody was asking me about quantum measurements of time, but what if we try to join general relativity and quantum mechanics together? So relativity and quantum mechanics are basically these two theories we know today that govern the world. We still don't know exactly how to join these two different theories and to obtain a relativistic quantum mechanics, a general relativistic quantum mechanics, so a single theory, but we do have some results. one of the results is that we get another wrong intuition, like the universe evolves, and it seems that this is false. We're not sure. I'm going to explain better this. But the fact is that if you take general relativity and quantum mechanics and put them together, one of the few results we know is the Wheeler-DeWitt equation. The Wheeler-DeWitt equation, it says H psi equals 0. Okay, you say, what does that mean? Well, okay, essentially what this means is that the state of the universe is stationary, so nothing happens in the universe, which of course is completely crazy because we see things happening all the time. So how can we interpret this equation? This equation tells us nothing should happen, but we see things happening. So this is what is called the problem of time in modern physics. There are many proposed solutions which are very technical and very complicated. I'm not going to talk about them. Part of these is something that also has to do with my own research. But what really this problem of time tells us is that we still don't really understand what happens when we join general relativity and quantum mechanics. It seems that the universe should not evolve, which is really weird. And I wanted to emphasize this problem of time because people have the wrong impression that physics is like a dead subject, something where we already have found everything. We don't have any more interesting open questions. Well, I would say this is a kind of interesting question because what physics seems to tell us is that the universe does not evolve, which contradicts everything we see around us. So, okay, this is a very nice question that we still have to work out. So what we saw by looking at what physics tells us about time is that all our intuition of time turn out to be wrong. And I'll read this passage from Carlo Rovelli's book. One after another, the characteristic features of time have proved to be approximations, mistakes determined by our perspective, just like the flatness of the earth or the revolving of the sun. The growth of our knowledge has led to a slow disintegration of our notion of time. All our intuition about time just disintegrates. What we call time is a complex collection of structures, of layers. Under increasing scrutiny, in even greater depth, time has lost layers one after the other, piece by piece. Okay, so all our intuitions, what I've shown you is that all our intuitions about time really go away when you think about this. So of course, this is going to make you wonder if all us physicists, maybe we are all completely crazy, or maybe we have completely lost touch with reality because we seem to say really very strange things about time, for example. Of course not. I'm a physicist. I am not crazy. Well, what would you expect that I would tell you, right? The truth is actually that it's necessary to abandon the limitations of our senses and our common sense to understand reality. So our senses and our common sense, which of course our common sense comes from our senses. So our common sense tells you a picture about reality, but this is false. And this actually is not a new idea because, for example, already Plato had very similar ideas. He was saying, okay, reality, we cannot really directly access reality. Reality is something, we are living in a cave and we just see the shadows of reality. Reality is outside and we cannot really access it. And the true scientists, here I put a picture of Marie Curie, one of the greatest scientists in the history of mankind. The true scientists know this. They have to study for years to eliminate their prejudices, their common sense against reality. So how does a scientist approach physics, for example? Well, remember the fish. And don't be a fish. You have to tackle physics, modern physics, with open mind. It's physics that is strange. So this fish has to open his mind in order to understand what a star is. It's mind-boggling to him. Now, for us, all these concepts that come from physics are completely mind-boggling in the same way. So it's very nice, this notion, I have to close my eyes to see. This is Paul Gauguin, je ferme les yeux pour voir, he was saying. So it's impossible to really see the results from relativity and quantum mechanics. You need to have really sophisticated experiments to see these effects. But you can use the eyes of your mind. You can help yourself with a mathematical formalism. The language of physics is mathematics. So here I've written the Schrödinger equation, this one, and the Einstein equations. These are the most important equations of quantum mechanics and general relativity. You don't need to understand what they mean, but these, I put them here just to show how physics, what is the language of physics? Physics proceeds through mathematics. Okay, so this basically concludes my seminar. So what did I say? Okay, I started from defining time in physics as either what is shown on a clock, this is one of the main notions of time, or a coordinate. These are the two main meanings of time in physics. These are not the only ones, like for example, somebody was mentioning thermal time. There are many other notions of time in physics. I've shown you how our intuitions are wrong about time. For example, time does not really flow. Another intuition we have is that the present exists. The past and the future do not exist. That's wrong. Past, present, and future, thanks to relativity, have the same essence, the block universe picture. Time travel is possible, although only theoretically, thanks to relativity. The universe evolves. Well, apparently, quantum mechanics joined with relativity tells us that this is not really true somehow. And I've also talked to you about the language of science. Science proceeds through mathematics, and this is how you really have to understand science if you want to understand science. So if you're curious, here I put some books you can explore about time. I left the Italian titles, but most of these books you can find in English as well. So just look them up. Okay, thank you.
Okay, thank you, Lorenzo. We have questions here. I must say that this Wheeler-DeWitt question has hit a lot, okay. Because the fact that the universe is not changing made arise a lot of questions. So, for instance, one of these is, but if universe is not changing, this means that entropy does not change, implying that the time does not exist. What is your comment?
Okay, so let me say one thing I should have said. Wheeler is dead now. Wheeler was one of the greatest scientists in last century. He didn't have that many original contributions. He was very prolific, but if you look at his students, a lot of his students won the Nobel Prize. A lot of his students gave very important contributions to physics. Kip Thorne, for example, it was one of his students. Richard Feynman was one of his students. I mean, so Wheeler is dead, so we can ask him, but we can ask DeWitt. And apparently, I don't know him, but one of my colleagues, one of my relativity colleagues told me that if you ask DeWitt about his equation, DeWitt is going to be very angry. He's going to say, oh, that equation is completely wrong. Okay. So this is one way of saying, but actually it's not so easy to dismiss the Wheeler-DeWitt equation, because actually it comes out, the way it comes out is by applying taking general relativity and applying constrained quantum mechanics to general relativity. It's a procedure that was developed by Dirac, and it's a very well-tested procedure which works very well, and that procedure is going to give you the Wheeler-DeWitt. Now, so the Wheeler-DeWitt equation, I would say, is correct. The problem is that you have to interpret it, because in the moment you say that the universe does not evolve, this is clearly wrong. I mean, it's clearly the universe does evolve. So you have to interpret what exactly this equation is telling you. And this goes back to the question that was asked. So one way of seeing it is that, okay, maybe the Wheeler-DeWitt equation is telling us something about the block universe. So the Wheeler-DeWitt equation expresses the state of the block universe. Of course, the state of the block universe does not evolve because it's a block. And the time is something which is internal to this block universe. Okay? So you have to consider an internal degree of freedom, which then does evolve with respect to something else. But if you look at the whole picture, there is no evolution. This is the idea. And this also replies to the question about thermal time. Okay, so the external time of the whole block universe is stationary, nothing happens. So also the entropy does not increase. But the inside the universe, the internal degrees of freedom do evolve, and you do have an entropy increase. This is one possible way of explaining the Wheeler-DeWitt equation.
Okay, good. There is a funny question from Lorenzo, who asks, how often physicists have to ask mathematicians for, let's say, when they find difficulties. So it happens that a physicist has to go to a mathematician to clarify the theory, to have the tools.
Well, it's a nice question, because what happens actually is that any physicist, including any theoretical physicist like myself, would like to have a mathematician to ask questions all the time. But on the other hand, you realize very quickly during your career that it's completely useless, because if you ask a mathematician, he starts answering in a way that it's completely useless to you. So you will not, that is not going to help you. So you have to learn, and this is a very big part of a theoretical physicist's job, you have to learn to understand enough mathematics to understand your theories, to develop your theories. And at the same time, it's very difficult to rely on mathematicians, because a professional mathematician is too abstract for a physicist, typically.
Okay. So another question is from Leonardo. So a photon going from Earth to the moon takes about 2 seconds. but how many seconds the photon itself see? I mean, how much time does pass for the photon? A tricky question.
Okay, yes, it's a tricky question, because if you take the Lorentz transformations, which would answer that kind of question, tells you like nonsensical results. They would just basically tell you that the photon sees no time at all, ever. So for the photon, no time passes. But it doesn't mean much, because a photon is not something that has a structure. So there's not a clock on a photon which can tell you the passage of time. So I would say this kind of question is kind of meaningless, because there's no way to find out the answer, because a photon cannot tell you that. And there is no degree of freedom inside a photon that can measure the passing of time.
Okay, so another question is why in the equations of relativity the space is described by real quantities, while the time must be described by a complex or imaginary quantity?
Okay, this is a way of formalizing relativity which works, unfortunately, only for special relativity. So in special relativity, you can formalize time as being imaginary and space as being real, but that is not going to work very well when you go to general relativity. So typically, physicists do not do that. But to answer this in a more deep way, technically, this is called the space-time signature, which is the fact that you have to treat time and space in a different way. Typically, you have a different sign, or you can use imaginary for time and real for space, or you can use negative sign for time and positive signs for space. The reason there is this is that, as I said, space and time are both coordinates, but you have to distinguish these types of coordinates. So space is a spatial coordinate and measures distances in space. Time is a temporal coordinate and measures temporal differences in time. So it's very important at the level of relativity to keep these differences in mind. And the way to do that is by using this space-time signature, or by using imaginary and real. So when we say that time and space are both coordinates in relativity, by no means we mean that space and time are the same thing. They are very different concepts, also in relativity. And the difference lies into this aspect.
Okay, so probably the very last question is from Miguel from Portugal. He asks you, what do you think about the M theory on 11 dimensions? Wow.
Okay, okay, this
you
is
have
not
1 minute only left, so
1 minute. This is not really related to my talk and to my research. String theory and M theory, I would say, at this point in time, currently do not look very promising as explanations for physics. I would leave it at that. Even people that work in string theory and M theory recently have started looking at application to solid state physics and to other branches of physics. It doesn't look very promising as a fundamental theory of physics at this point.
Okay, So I think that we can close here. Thank you very much, Lorenzo. It has been really inspiring how our school is named, INSPYRE. And we have a lot of questions. Of course, we couldn't answer to all. Probably we will try to answer to some more offline. And so I thank you again, also on behalf of all the students that are at their home. And see you tomorrow. Bye to everyone.
Okay, goodbye.